All right, so we're on to question 7. There are 1, 2, 3, 4 A, B, C, D equations that we're asked to solve. Um, it says solve each equation for x. Okay. And it says check your solution. So I will definitely be demonstrating how I check my solutions on the calculator. Basically, I'm just verifying that the left and right hand side are the same. It doesn't need to be super involved, and if you just give me the value that the left and right hand side become, um, when you check it, I'm satisfied with that. And really, I mean, I want you to get these answers correct, and I know that you guys want to get the answers correct. And what I'm saying is, if you attempt to check an answer and you don't get that the left hand side and the right hand side are the same, that means that there's an error, and that's the fun part, right? Honestly, that's kind of an interesting thing, is trying to go through and figure out perhaps what you did wrong. So let's take a look at part question A here, and my favorite technique for this is still using fraction busters. I like the name of it, and I am not someone who's incredibly fond of fractions, and I like doing this. So if you want, you can say, look, I'm gonna bust up the fractions in 2 steps. You could multiply by 3, and that would take care of this fraction and this fraction. Well, those denominators would go away. And then you could multiply by 2x, and that would take care of that. But may I suggest, if we multiply by 6 times x, right, on each side, we're going to push a factor of 6x through both the left-hand side and the right-hand side. It's going to eliminate all the fractions. So I like to be real explicit when I write this out. So I'm just going to write 6 and then times x and then times 15 and then over 2 times x plus 6 times x times 7 over 3, and then that equals, I'll just put on this side, 6 times x times 8, all divided by the number 3. So what's beautiful about this, it doesn't look great yet, but it's coming, right? We're going to be here very soon, and the reason why is there's all kinds of ones that we can eliminate. So some of them are quite actually, only one of them is obvious, right? You can clearly see that there is an x divided by an x here, so that one's gone. But 6 divided by 2 is 3, right? So in this, I'm looking at, this is going to be 3 times 15, right? And yeah, I would write that step just because I can see where the 3 came from. 6 divided by 2 is 3, and then there's a 15 that came down. So I can just kind of visualize it better. The next term over, if I take 6 and I divide that by 3, it becomes the number 2. So this is going to be a 2 times x times 7, which is 14x. So I've got a 14x. And on the other side, 6 divided by 3 is 2. So that becomes a 2 in the numerator times an x times an 8, which is 16 times x. So look at this. This is already, it took a few steps, but this is so much less intimidating than the original equation, right? There's nothing here that scares me. I can look at it and I can see that I'm immediately going to take away 14x from each side. That's going to give me that 45 is equal to 2x. And as I divide both sides by 2, I get x is going to be 45 halves, right? That's the value of x. So I'll just write it here. X is 45 over 2. And I know some of you just can't resist. You have to write it as 22.5, and that's okay. But this is clearly the more beautiful of the two answers. I say that and like, well, is it easier to check? Actually, 22.5 is probably an easier answer to check. So let's see if we can efficiently check that question using our calculator. So it's 45 over 2. So I'm going to, on this ROM, I can use the fraction key. So I'm going to start with a fraction. So I'm going to hit alpha and just grab a fraction. And in fact, I'm going to go down into the denominator. I want a fraction in the denominator as well. It's going to be, well, let me put the 5 up here. So I've got, 15. I'm going to go down here. There's going to be a 2. And then I'm going to multiply by another fraction. So I'm going to go grab another fraction. There we go. And for this fraction in the denominator, it's my answer. I'm going to put x there, right? And x was 45 divided by 2. So I'll just say 45 over the number 2. So if you look at it, it looks great. It's fun, fabulous, right? I've got 15 over 2 times x, and x is 45 has, right? That's what it was, right? Yeah, 45 has, or 22.5. Now, if I take that and I add to it another fraction, so I'm going to alpha fraction, and the fraction I want to add to that is 7/3. And I'm going to evaluate this expression. What? It's 8/3. That's so cool that it even leaves it in fractions. So I can see, yes, 15 over 2 times x plus 7/3 is indeed 8/3, right? This is exactly the answer. So that checks perfectly. And I can move on knowing that I've got that one right. Take a look at what you did on the test. Some people did some very interesting things, and if you contend that, hey, you've got a clever shortcut and that your way works, come talk to me and I'll try and explain why what you wrote doesn't follow logically, right? It's not truthful. Not that you're trying to lie, but it's not truthful what you wrote. So we'll look at that and see if we can figure it out together. I'm going to simplify this by subtracting 5 from both sides, right? I don't want to have to deal with trying to square both sides. Squaring this side, and I think some of you did that, would literally involve this, and then you didn't do it correctly, right? So squaring something is a little bit more complicated than just squaring each of the parts. You have to square it, and then it's a binomial times a binomial can get ugly. But we don't need that ugliness. We can just look at the square root of 3x plus 12 on one side, and over here that's just going to equal 10. Well, this is fabulous, right? This is great because I know my perfect squares and square roots. I know that the only way that I can get an answer of 10 when I take the square root of something is if this thing was the number 100, right? And our textbook calls this looking inside. I look inside and I know that 3x plus 12 has got to be the number 100. And it's also the case that if I square 10, I get 100 over here. And if I squared 3x plus 12, I'm just going to say if I square the square root of it, I'm going to say I get 3x plus 12, and I won't say any more than that right now. So to solve this, I'm going to take away 12 from each side, so this becomes 3x is going to equal 100 minus 12, I believe, is 88. And next, I just need to divide both sides of that by 3, so x is 88 thirds. And I know that you can't leave it alone. You're not happy with that answer, so I'm okay with 88 thirds. I'm also okay with 29 and 1/3, so that's 29 plus 1/3. Make sure you understand that. And I'm also okay with 29.3, provided that you indicated that it repeated, right? If that was lacking, I might have deducted a point. So this right here is always the preferred answer. And look at it. It's what we ended up with. It's the simplest of the three. Now let's go back to verifying here. So if I take, and I'm going all the way back up to the very original equation, right? If I go up here and I look at the square root, so let's grab a square root, and then I want 3 times my answer, and I'm going to grab a fraction to do that. So I'll hit alpha y equals, there we go. And my fraction is 88 thirds, so I'm going to go 88 over 3, perfect, and then plus 12, and now I'm going to leave the radical and add a plus 5. Okay, so take a look at it. You can see the radical ended right there at the 12, and then 5 is added outside of it. So this is 3x plus 12, the square root of 3x plus 12, and then plus 5, and when I press enter it should say 15, and it does. It does. So what we have here is a solution that has been checked. It definitely makes both the left-hand side and the right-hand side equal to 15. All right, question C. So I see the 27 and I see the 3. 3 is the smaller of the two. I might play with these and just see, but 3 to the first power is 3, 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81, 3 to the 0 is 1, 3 to the negative first is 1/3. Why are you writing all these? I'll stop. I just want you to see that, depending on the bases that you're given, right, there's definitely a relationship between these. It's built on factors of 3, powers of 3. 27 and 3 are. And as I've told you, the only way that I'm going to ask these questions right now is if you can get it so that the bases are the same. I'm not expecting you to solve these using logarithms or anything like that. So if you look up an equation like this on Khan Academy or Wikipedia or something, they may suggest using logarithms. Or if you've got a father who's a structural engineer or mom's works for Caltrans or something, they may suggest other tools to you. That's not the intent right here. We're just solving these by switching these so that the bases are the same. And then once our bases are identical, it has to be the case that the exponents have to be equal. So here's our strategy. I'm just going to notice that 27 is the same thing as 3 to the third. So I'm going to rewrite this as 3 to the third, and I'm going to raise that to the x plus 1 power. So if you look real carefully, what do I have? I've got 27 to the x plus 1 power. Now, the other side is already a base of 3, so I'll just write this as 3 to the 2x minus 4 power. Now, there's a little thing that some of you are missing. So if I have, for example, a, and I raise that to the b power, and then I raise that to the c power, this is a to the b times c power, right? So there's multiplication that happens there with the b and the c. I multiply b times c. What I've observed some of you not do is you're not distributing this 3 to both the x and the 1. You're not multiplying it to both of them. So this becomes, right, 3 to the 3x plus 3. So notice how both of them, both the x and the 1, were multiplied by 3. And over on the other side, this is 3 to the 2x minus 4. So I've said it before, I'll say it again. The only way that these can be truly equal, right, with both having bases of 3, they both have a base of 3. The only way that they can ever be equal is if the exponents are identical, right? So I just say to myself, well, let's just make that happen, right? What value of x makes them identical? Well, let's find out. We're just going to set this exponent equal to the other exponent. And this will allow us to answer the question, what value of x will make this exponent equal to this exponent? Because that's what we want. If I take away 2x from both sides, this becomes an x plus 3, and this is negative 4. And if I take away 3 from both sides, I get x is negative 7. So this value of x will make both the left-hand side and the right-hand side equal. Let me write that down. X is going to be negative 7. So checking this, that's a little interesting, right? So it's not difficult, but it's a little funky. So let's do this. So let me go 27, and I'm going to raise it to the power of. Now, this particular calculator is cool because it's going to stay in the exponent until I tell it to leave. On some calculators, you may need to use parentheses here, but I'm just going to say 27 to the negative 7 plus 1 power, right? Or 27 to the negative 6 power. When I do that, take a look at the number, right? 2.58 times blah, 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 blah. Let me write down what that is. That is 2.58 more decimals times 10 to the negative 9th power. So it's written in scientific notation. If I wanted to write it out all the way, I would have to move this decimal place 9 places this way. So it's a very small number, a very small number. So let's do the same thing with the other side and verify that we get the same value. So on this side it's going to be 3, and then I'm going to raise it to the power of 2 times, I'll do negative 7, and then minus the number 4. So that's 3 to the 2 times negative 7, 3 to the 2x minus 4. By the way, you can see multiplication. There's this star character that shows up. That's what we use. When I press enter, lo and behold, it's the exact same very small number, right? They're both about 2.58 times 10 to the negative 9th power. So negative 7 is exactly the value that will make the left and the right hand side of this equation the same, and the same value they are is this extremely small number, 2.58 times 10 to the negative 9th. All right, final problem in this question. Solve for x. and you can see that I need to multiply this binomial times this binomial. My recommendation is, well, there's shortcuts for this, and probably at a certain point, binomial times a binomial, you'll probably might embrace a shortcut. But if you're looking at a trinomial times a trinomial or something, seven terms times three terms, try and use this generic area model because it really organizes your work. So across the top, I've got a 2x plus 5, and then I've got this x plus 5. The parts here are this is a 2x, this is squared, and this is a single x. That's 1 times x is x. 2x times 5 is 10x, and 1 times 5 is just the number 5. So that is, equivalent to all of this. So I'm going to rewrite that part of this equation. I will rewrite it as 2x squared plus 11x plus 5. I hope you can see that the 11x came from the fact that I'm adding an x and a 10x together, and that's why I end up with 11x. And then you can see the 2x squared and the 5 in the generic area model. So, one of them is showing the area as the product of the length and width, and the other one is the area expressed as the sum of the parts here. Let's continue with the equation. So there is a plus 3x that I need to make sure I don't forget and write down. And then on the other side, this equals 2x squared plus 21. So the happy news is that on each side I've got a 2x squared, right? So I'm going to subtract that from each side, which makes the equation a little easier to deal with. Also, I'm going to combine the 11x and 3x and write that as 14 times x. So I've got 14x plus 5 equals the number 21. I'm going to subtract 5 from each side, and when I take away 5 from 21, it'd be easier if it was taken away 7. It'd be 14. But if I take away 5 from 21, I believe I get the number 16. So take away 5, 14x equals 16. All right, and then as a final step, I'm going to divide both sides by 14. So 16 14ths. However, it just triggers that both of those have a common factor of 2. So there's this lurking giant one of 2 over 2. If I remove that, divide both of those by 2, I get an 8. And 14 divided by 2 is 7. So x is 8/7. Let's write it down here, 8/7. And then let's check this. Unfortunately, this is kind of a long expression to check 8/7, isn't it? Yeah. It's kind of long. Something occurs to me. If I hit alpha, grabbed a fraction and hit 8, and then over 7s, I think I can take that and I can store it in. Let's see. I can store this in. I can't exactly remember how this works. Let me see. Store it in alpha A. Okay. So if I hit alpha A and press enter, it reports that that's 7 or 8/7. So I can do alpha A to bring back up the 8/7 because it's appearing so many times. So let's do open parentheses 2 times, and I'll just do A, right? And then plus 1, close the parentheses. So that's 2 times A, which I stored 8/7 in. So that's 2 times 8/7, close parentheses, times, I'll do alpha A again, plus 5, close the parentheses, and I'll go times 3, or plus 3 times A, so I'll bring up alpha A. So that's one side of the equation, and let me go ahead and press enter and see what it gets us. It gives us, that's cute, 1,157 over 49. Huh, I like it. I'll leave it for a minute. Let's see if we get the same thing on the other side. So on the other side, we're going to go 2 times, well, actually, I don't have to hit times. 2, I should be careful. I think this will do this the right way. 2a, and then I need to square that. So this calculator should know that it's just the a that's getting squared. So that's 2a squared, and I leave the exponent by hitting this right arrow key, and then I just add to it the number 21. So let's press enter, and yes, it is also, 1157 over 49. So this value of 8 sevenths is spot on because it makes both the left and the right hand side equal um, 1157. By the way, if you wanted to convert that to a decimal, I think if I hit math, yeah, number 2 is kick it to a decimal, so about 23.6. So that is rather extensive, but that's the end of question 7. And I hope that you look at that what I'm doing there with the check. I know it's a little time consuming, but it's an important thing to kind of look at and see what's happening there. When you look at this, you're like, Mr. Roberts, it took you 20 minutes to do this problem. Well, I guarantee you, if you're doing these problems, this should easily be able to cut in half. It takes me longer because I'm talking about things and showing every step, but I think this is a problem that should take about 10 minutes in order to complete.